Have you ever wanted a day to go by faster? Perhaps you're taking a test and you finish way too early and all you can do is stare at the wall. Or you're hanging out with your friends and you're about to go home, but you just want to stay in that moment with them. But time's constant and doesn't change. Well, I'm here to tell you that's actually not true. But before we can understand how time changes, we have to understand how motion changes depending on where you observe it from. Here's a visual example.
Now relative to you, I'm moving, but your surroundings aren't.
Now that you're in the moving vehicle with me, we appear stationary to each other, but our surroundings aren't. That was a simpler example, so it could be confusing how that could ever relate to time. So here's another example. Picture this, you're standing on a train platform, viewing someone through the open window of a stationary train, bouncing the ball up and down. If the train moves to the left, the ball now will move in a diagonal motion to the right. The ball is no longer going straight up and down, but in a triangular motion. And because the longest line on a right triangle is the hypotenuse, the one that goes diagonally, the ball takes ever so slightly longer to go from the floor back up to the person's hand, making time seem as if it has slowed. But the person on the train wouldn't experience the same phenomenon. The person on the train would see the ball going up and down, just as if the train wasn't moving on, like when we were in the car earlier. This makes it appear as though time is different for the person on the train and the person on the station, and this is an example of time dilation. These short experiments provide us with an example of special relativity, which is a theory of space-time published by Albert Einstein in 1905. Special relativity has an inertial frame of reference, which is a reference point that is non-accelerating. The person viewing the moving car earlier and the person viewing the train are these frame of references. But what if the object that is being observed is moving unimaginably fast?
For example, picture a similar situation as the train from before, but the person bouncing a ball is no longer on a train, but on a spaceship traveling 99% the speed of light. If the ball appears to take more time on the train, imagine how much longer it takes barreling across space nearly at the speed of light. It would almost be completely still, and the person inside the spaceship would see the universe flying by.
For the observer, it appears as though time has slowed for the space shuttle, but for the person inside, it's remained the same. This means that time is essentially separate for the person viewing the shuttle and the person inside. The person inside could travel at 99% the speed of light for about 5 years and come back to an Earth that is 36 years older than when they left it. This is an example of time dilation due to special relativity, which is what we discussed earlier, but this is on a greater scale. Now, the next time that you want to skip a test, just hop in a space shuttle traveling at 99% the speed of light for about 52 minutes, and you can skip the whole school day.